We then focus that in our lower resolution, high speed, low speed. These are different types of rubber. So we are based in Scotland. So we make and measure rainbows, manufacture complete hyperspectral imaging systems, which simultaneously record spectral and spatial information across a wide spectral range, so all the way from the visible or even the UV to the shortwave infrared, so from around 300 to 2500 nanometers. And that's super useful for a range of different industries because you can analyze both spatial characteristics of samples, so size, shape, distribution, stuff like that, and all sorts of applications. So you can do those spatial measurements, but you can also do chemical measurements. So in the infrared, you can measure, for example, here we have various different types of rubber and plastic. You can easily differentiate different types of plastic based on different polymers. Even if those types of plastic are visually the same, exactly the same color, if they're a different type of plastic, it's easy to differentiate with the infrared. In the visible, going in the other direction, you can do very, very accurate color differentiation. So if you have, human eye can typically detect a delta E, so the difference in color of two shades of 1 to 2 delta E. With a visible hyperspectral camera, it's typically 0.1 to 0.2, so a 10 times more efficient measurement. Okay. And the reason for that is super high spectral resolution. So the visible camera has a spectral range of 400 to 1000 nanometers. Mm-hmm. And within that range, we get a data point every 2 nanometers. Mm-hmm. So in the visible spectrum, we get roughly 300 wavelength points every single pixel. So we acquire photorealistic images of whatever we're measuring, any application. So you get a visual representation of your sample, as you would with a standard RGB camera. But behind every single pixel, every point on that, you have 300, or if you have 2 cameras, you have 600 data points, which gives you the ability to differentiate very, very closely related materials based on both color and chemical information. No worries. So we make the measurement, as I said, so we get spatial, so we get a photorealistic image and we get spectral information. So what that means is, if we have our data set, we can scroll through each individual wavelength image and visualize the image at that wavelength. So we can see
which one gives you the most contrast.
Exactly. So we can see also where the inks in this particular object become invisible. So at around 700 nanometers, the dyes in this, I think it's a cloth for cleaning spectacles, these become invisible, so you can see that. But what the super valuable thing is about this is that at any point, I can measure the optical spectrum. So that's the spectrum of that square, or I can measure this one, or this one. Or I can do it in real time. So I can measure the spectrum at any individual pixel position. So I can automatically identify different colors, different materials. So if I go to the infrared...
So basically this is a way to define the spectral signature for a material?
Exactly.
So it gives you a tool and you know this is the signature for this, so that you can...
So for example, for these are different types of rubber. So you can identify based on the unique spectrum of these, which is here. We call these spectral fingerprints. So just like if I commit a crime and my thumbprint was captured at the scene, the police could identify me as the perpetrator because my thumbprint is unique.
Unique to you, yeah.
This series of, we call them absorption features, exactly, is unique to this material. So based on that response, we can automatically identify this as rubber type A, rubber type B, rubber type C, and so on and so forth.
So this is a pretty big camera. So tell me a little bit about why is it so big? What's inside that
Sure. So
big box?
So the configuration of a spectral camera, or actually a push broom spectral camera. Push broom is an industry term for line scan. So we're measuring one line frame at a time. So that's why the sample translates under the camera. So in here we have the lens on the front of the camera, which is specified focal length. Just like a normal camera, you can interchange the lens and measure things at higher resolution or lower resolution, high speed, low speed. In front of this, we then have the collimating optics, which focuses onto the spectrograph, which then takes the white light from the lamp and splits that light into the hundreds of colours of the rainbow. We then focus that light from the rainbow.
There's some light grading.
Yeah, exactly. It's a spectrograph in here. Then we have another lens which focuses the rainbow onto a focal plane array sensor, which then we record this. So you have sensor, spectrograph, entrance, slit, and lens.
Got it.
And it's the same for all cameras. And the great thing about this is that there's no moving parts. So the maintenance of these cameras is literally zero.
Okay.
Super robust. And these can be applied to laboratory and industrial. So we are based in Scotland, so the land of whiskey and haggis and kilts.
Yep.
Specifically in the city of Glasgow.
Did you know India is the biggest consumer of whiskey?
I did know that, yes. Yeah.
So I guess that's why
very good customer of ours, yeah. We've operated in India for many, many years.
Oh, okay.
So
what kind of applications, in which industries?
Various applications. So in the past, although our company now is focused specifically on hyperspectral imaging, in the past we've manufactured systems for light measurement or light sources, so monochromators, fluorimeters, and also tunable light sources, as well as HSI systems. And they've been deployed into a range of academic and industrial applications.
Academic and industrial. Okay.
Yeah, and also industrial customers, which is more of a sensitive area for data sharing and stuff like that.
Right.
Various universities,
okay,
the IITs, several, all over.
Got it.
Our technical director, who's been the director of the company for I think over 20 years, he founded the company. Done business in India for almost his entire career.
Oh, wow, okay. Great.
All over India. Myself, I've sadly never visited.